listeners, you are welcome to this episode in our channel, African Science and Humanities Review. In the last episode, we started with the laws of thermodynamics. There are three laws: the Zeroth law, the first law of thermodynamics, the second law, and the third law. We were only able to treat the Zeroth law in that last episode. And the Zeroth law deals with the concept of transitivity in the sense that you have a system A, which is in equilibrium with a system C. And I have another system B that is in equilibrium to another system C. Then you can say that the system A is in thermodynamical equilibrium with system B. That's essentially what the Zeroth law of thermodynamics says. Today we are going to continue and we are going to look into the first law of thermodynamics, the second law of thermodynamics, and the third law of thermodynamics. Don't forget that by talking about thermodynamics, we are talking about the dynamics, the motion related to heat processes. I believe you are going to enjoy the episode. You are welcome. Thank you very much. First law of thermodynamics. This first law of thermodynamics actually deals with conservation of energy. In the sense that it considers the energy that flows inside a system and the energy that flows outside the system. And as we know, with respect to the conservation of energy, the total amount of energy is conserved. It's never destroyed. It can be transformed from one form to the other, e.g. potential energy to kinetic energy, but the total amount of energy remains the same. So the first law of thermodynamics, which is also the law of the dynamics of heat processes, actually describes the equivalence of energy in thermodynamic systems. That is essentially what the first law of thermodynamics describes. It just tells us that within a thermodynamic system, there is conservation of energy, whereas you consider the energy that flows outside, which we have called the outflow here, energy outflow, or the energy that flows inside. If there is no energy that flows outside, then you are having the total energy will be the sum of the energy inside. If energy flows both from inside and outside, then the total amount of energy will be the sum of the energy that flows outside and the energy that flows inside. But whichever way it is, the first law says that the total amount of energy is constant. It's never destroyed and to remain the same. It may be converted from one form to the other, just as we know in the general principle of the law of conservation of energy. So that is what the first law of thermodynamics says. It just describes equivalence of energy systems in the sense that energy can never be destroyed. Then, before we consider the remaining two laws, the second law of thermodynamics and the third law, we want to briefly explain the concept of entropy. Entropy. This is a very important concept in thermodynamics, and in one of our episodes we mentioned that when you talk about thermodynamics, another field of study that is synonymous with thermodynamics is statistical mechanics or statistical physics. And when one goes to that field of study, discover that you make use of a lot of statistics, probabilistic description. Because when you talk about thermodynamics, thermodynamics processes, it has been observed that the processes are mainly non-deterministic. They are probabilistic in nature. So the concept of entropy just describes, measures the degree of disorderliness or uncertainty of a given thermodynamical system. Indirectly, it is the energy which is not available for work. So that is entropy, because we are going to use the concept of entropy subsequently. And of course, there is a particular concept in thermodynamics, in statistical physics, the concept of chaos. Chaos is not exactly the same as entropy, but it has a strong link with entropy. Chaos just describes a system that has high entropy. So you can use chaos, the concept of chaos, just like the familiar concept of chaos. There is a lot of perturbation, there is disruption in the system. So chaos describes a system that has high entropy. But entropy, when you use entropy generally, it may be high or it may be low. Entropy describes a measure of the degree of disorder in a system. So with that, we can now consider the second law of thermodynamics. Remember, we started with the Zeroth law in the last episode. Now we're considering the first law, the second law, and the third law of thermodynamics. To clearly understand the second law of thermodynamics, we can look at this simple sketch. We have a system A. Of course, when we say system A thermodynamical system A system that undergoes thermodynamical processes. Okay, we have explained the concept of thermodynamics, just the dynamics of heat processes. So supposing I have a system A here, it is actually an isolated system in the sense that the system exists on its own. You can, for instance, you can consider you have you can have a two-burner stove. You put your pot of water on one, and you put another kettle or pot of water on the second one. So the first one that is on its own, it doesn't have any link with the other one, is a system that is in thermodynamical equilibrium with itself. So we are using this to show it is in equilibrium with itself. When you say something is in equilibrium, thermodynamics is at stake, is at rest. It doesn't, and the fact that it is an isolated system means that it doesn't, so to say, to a large extent or theoretically, it doesn't have any link with another system. So that is the system A. Indirectly, system A obeys the concept of reflexivity in the sense that if I have a system A that is in thermodynamical equilibrium with itself, then we can say that that system, if I define a relation on that system A, then you can say that that system is in thermodynamic equilibrium with itself. So that's what is called reflexivity, in the sense that when I have a relation and I define it on a set or in a system, and that system on its own obeys the relation A in relation to A, where the relation is what you have defined as the system is in thermodynamic equilibrium with itself. So if A is in thermodynamic equilibrium with itself, indirectly we are saying that A will always be in thermodynamic equilibrium with itself. So that is the concept of reflexivity. So we have a system A which obeys reflexivity with respect to thermodynamical equilibrium. So that's the first condition to understand the second law of thermodynamics. Then you also have another system, B. Just as I've used the two-burner stove, you have your pot of water, your kettle of water in one, your kettle water in another, such a way that they don't have any interaction with one another. So the system B, just like system A, is also in thermodynamical equilibrium with itself. So it is said that we say that it follows the reflexibility rule with respect to thermodynamical equilibrium. And for system A, we have denoted its entropy, that is, its degree of disorder of this system, the degree of uncertainty of this system by E1. And we have denoted the degree of uncertainty of system B by E2. Of course, at this junction, I just need to explain that why we still, just in line with what my earlier explanation, that this, you can see uncertainty here, and anywhere you see uncertainty, and you want to use mathematical notations to describe, then you have to think first about statistics, mathematical statistics, because that's where you have probability that deals with uncertainties. So you have system A, that's the condition 1 for second law of thermodynamics. A is in thermodynamical equilibrium with itself, and it has the entropy E1. B is also in thermodynamical equilibrium with itself, it has entropy E2. Then the third condition, before we get to the results of the second law of thermodynamics, the third condition is this, which we have called condition 3. The third condition is that there is now interaction between this our system A, which is in equilibrium with itself, with system B, which is in equilibrium with itself. So we have used this plus to show that system A interacts with system B. Here, there was no interaction at all. They were just existing in isolation on their own. But here, we decided to, you now interact when there is need to make A and B to interact together. We make that a condition 3. Then we can now get the result for the second law of thermodynamics, which says that 1, the first result, we have up to 3 results with respect to second law of thermodynamics. The first one, the second law says that given this condition 1, A is in equilibrium with itself, condition 2, B is in equilibrium with itself, and condition 3, A is interacting with B. Then we can say comfortably that system A is actually in equilibrium with system B. That is the first result of the second law of thermodynamics. A is in equilibrium with itself, B is in equilibrium with itself, then, and thirdly, A now interacts with B. Remember here, they were not interacting. A was existing as an isolated system, the same thing with B. But if you now bring the two systems together to interact, then we can say safely that system A is actually in equilibrium with system B. That's the first condition, the first result of the second law of thermodynamics. From there, we can move to the second result of the second law of thermodynamics. The second result of the second law of thermodynamics actually describes what you expect the entropy of the combined system A and B to be after they have interacted together, given the condition that system A has entropy E1, system B has entropy E2, and we represent the entropy of system A and B together interaction by E3. Then you can jump to the conclusion and say that the entropy of system A plus the entropy of system B must be less than or equal to the entropy of system 3. That is, the degree of disorder of system 1 plus the degree of system disorder of system 2 is going to be a numerical value, must be less than or equal to the degree of disorder of the interacting system. Of course, we should take note of the fact that we have less than or equal to. So shortly, we are going to see when this inequality can go for equality. This one is saying that E1 plus E2 is less than E3, or E1 plus E2 is equal to E3. So when can we have a situation in which we can say with definiteness that E1 plus E2 is equal to E3? So that is going to lead us to the third result with respect to the second law of thermodynamics, and result 3. So it now says that if all the intensive variable of system A, by an intensive variable, you can talk about like your temperature, like your pressure, okay? All the variables that have effect on system A, okay? So if all the intensive variable of system A are the same as the intensive variable of system B, then that can give us an assurance that in actual fact, the entropy of E1 of system A plus the entropy of system B must be equal, exact equality to the entropy of the combined system A and B. So the result enables us to be able to determine what happens to an interacting system or a group of interacting systems. That's the interacting thermodynamical system. That is what this second law treats. So you can have E1 plus E2 with E3, provided that the intensive variable of system 1 is equal to the intensive variable of system B. System A is equal to the intensive variable of system B. And that now leads us to the third law of thermodynamics. The third law of thermodynamics. So remember we said first law, second law, zeroth law, first law, second law, and then we are now about to describe what the third law of thermodynamics says. So for the third law of dynamics, to understand it, you have to understand the condition of the law, then the result. The condition says that we're given a system. It could be a system A that we have been using, or a system B, or it could have been a combined system A and B that have interacted, and then you have added a new system C. But you just have a system, and if you represent E to be the entropy of that system, and the T to be the temperature of that system. So the third law says that if the temperature of that system you are considering tends towards the absolute zero, and what do we mean by the absolute zero? We are referring to the ground state, that is to say, the state of minimum thermal energy of that system. The temperature tends towards that, towards the state of minimum thermal energy of that system, then you can conclude safely that the entropy of that system you are considering actually tends towards a constant. That is going to be a number. A number is not going to be a variable. It's going to be like 1, 2, 3, 4, 5. It's not going to be a variable. You are sure that it's going to be a constant, provided that the temperature, which is an intensive variable, tends towards the ground state, that is the state of minimum thermal energy of that system. Then you can say that the entropy, the degree of disorderliness or uncertainty of that system, will tend towards constant K. That is to say, it's going to approach constant K. So that is what the third law of thermodynamics teaches us. I believe you have enjoyed today's episode where we treated the first law of thermodynamics, the second law of thermodynamics, and the third law of thermodynamics. That means we have treated all the relevant basic 4 laws of thermodynamics, that is to say, the zeroth law of thermodynamics, the first law of thermodynamics, the second law of thermodynamics, and the third law of thermodynamics. I believe you have enjoyed today's episode. Please stay tuned for the next episode on this channel, African Science and Humanities Review. Thank you very much.